welcome you all for the course Digital Principles and System Design. Today we are going to discuss about another kind of a synchronous counter. In the previous class we have started discussing about the counters. Counters can be designed in two ways. Synchronous counter, the other one is called as an asynchronous counter. Synchronous counter is a circuit in which the clock pulses are applied simultaneously. Okay. In the last class, we have designed a counter using JK flip-flop. That is, we have designed a modulo 5 counter using JK flip-flop. You should not assume that counter will always design a counter in some fixed sequence or fixed series. You can generate any sequence using any kind of flip-flop. That's what we are going to see in this session. Today, we are going to design a counter that generates the following sequence, that is 1, 3, 4, 6, 7, once again 1, that is the reset state, which is nothing but it is going to repeat the sequence once again. So this sequence we are going to generate using a T flip-flop. Remember, for designing a counter you should know the excitation table, excitation table of a specific flip-flop by which you are asked to design a counter. Okay, here we should know the excitation table of T flip-flop. Not only the excitation table, we should thorough with both the excitation table and characteristic table of a specific flip-flop. Okay, while designing, excitation table will be useful. After designing a counter, for verifying whether the desired sequence is being generated by a desired flip-flop, we are in need of a characteristic table of a flip-flop. So, for designing counters, we should know both excitation table and characteristic table of a specific flip-flop. Okay, as I already told you, any counter designing involves 3 steps. First, you should know the excitation table of a specific flip-flop. Then, you should write the input sequence table. Okay, followed by you need to find the input for each and every flip-flop. Then finally you need to end up the designing with the circuit. Okay. So now we are going to design using T flip-flop. Excitation table is for the T flip-flop is QT plus 1 and T. 0 0 means 0, 0 1 is 1, 1 0 is 1, 1 1 is 0. Okay, using this excitation table only, we are going to construct this input sequence table. We know the input sequence. What is the first state? 1. Okay, 0 0 1. Then there question arises. How I am designing? It is a 3-bit. As I already told you that you should look at the maximum value given in the sequence. Here the maximum value given in the sequence is 7. How many bits are required to represent 7? 3 bits. So obviously you need to represent all the other values with using 3 bits. If 3 bits are required, how many flip-flops are required to design this counter? 3 flip-flops. Once again I will repeat. If there are n bits, then how many bits are required to? How many flip-flops are required to design means n flip-flops. Okay. Here we are representing each state in terms of 3 bits. For this problem also we need 3 flip-flops. Okay. Right. So input sequence A, B, C. First state is 1, that is 0 0 1. Second state is 3, 0 1 1. Then 1 0 0, 1 1 0, and then 1 1 1. Once again, this is the reset state, that is 0 0 1. Okay. Now look at the column of A. Present state is 0. Next state is 0, which means that 0 0. What is 0 0 here? 0. So that is why I have put 0 under the flip-flop input counter TA. Okay. Then you compare these two values. 0 1. 0 1 means what? 1. 0 1 means 1. Then 1 1. 1 1 means what is 1 1? It is 0. 1 1 means 0. Once again, this is also 1 1 0. 1 0 1 0 here is 1. So that is why it is 1. Similarly, you have to form the values for TB using the column B. 0 1 1. 1 0 1. 0 1 1. 1 1 0. 1 0 1. Okay. Similarly for the last column called as C. 1 1 0 1 0 1 0 0 0 0 1 1 1 1 0, right? So how I am saying is this, we have to assume this as the present state and this as the next state. Similarly, for finding the next value, you have to assume this as the present state and this as the next state, and so on. Based on which only we are finding the input, finding the values for D. Okay. What is the next step? We need to construct the Kmap for each flip-flop. Each flip-flop inputs, that is for TA. First we have to find for TA. Okay. So 3 bits. So obviously we are going to use 3 variable Kmap. 3 variable means how many cells will be there in the Kmap? 8 cells, right? A, B, C. And one more thing is 3 variable map means there will be in totally 8 combinations, starting from 0 to 7. If any of the inputs are not the part of the sequence, we have to assume that input as the don't care. For those input, we have to put don't care as the output. Okay. For example, here we need to bother only about 1, 3, 4, 6, 7. We need not to bother about the inputs 0 to 5. Then we have to put don't care for the input 0 to 5, right? 0, 2, and then 5 don't care. Okay. Okay. Then now we will look into the actual inputs. 0, 1, 1 is 1. We won't bother about the value of 0 in the output. Okay, 0, 1, 1 is 1. I put here. Similarly, 1, 1 is 1. 1, 1 is 1. Okay, I think here there is no need of using your don't care. Only one pair is coming. Okay, what is TA? We'll write it here. What is TA here? So A won't come. This alone is coming, which is nothing but BC, right? So we'll write TA equal to BC. Okay. Next we are going to find about TB. We are going to find it for TB. So 0 to 5 is going to be common, right? 0 to 5 is a don't care term for all the T flip-flops. What is TB now? So it is 1 for 0, 0, 1, it is 1. Then 0, 1, 1, it is 1. Then 1, 0, 0, it is 1. And then 1, 1, 1, it is 1. Okay. 1, 1, 0, it is 0, we won't plot it. Okay, then how we can find it now? I think we can form 2 quad here. That would be better. Yes, I think you can form a 2 quad. Yes, this 2 quad we can form. Now we'll see what is the value. So TB. First we'll see this quad. A won't come. What is the common bit here? 0. 0 corresponds to B. Then it becomes B dash. Plus, if you take this quad, A won't come. What is the common bit? 1. 1 corresponds to C. So then TB is B dash plus C. Is it? Next we are going to find the expression for TC. Already told that 0 to 5 are the don't cares, right? look at the actual input. 0, 0, 1 is 0, we are not going to plot it. 0, 1, 1 is 1, 0, 1, 1 is 1. Okay, 1, 0, 0 is 0, we are not going to plot it. 1, 1, 0 is 1, 1, 1, 0, it is 1. Okay, then similar triple 1, triple 1 is also 0, we are not going to plot it. Clear? So now we are getting only these two pairs, this one and this one. For this pair we'll be getting A dash. What is the common bit here is 1 is common, that corresponds to B, so that is A dash B, plus for this pair A won't come, we will get only 1 0, that corresponds to B C dash. So we will be getting B into A dash plus C dash. So therefore PC equal to B into A dash plus C dash. Okay. Now we need to design the counter. These are this expression that we have found out for TA, TB and TC. Okay. So TA, there will be two outputs for every flip-flop. Inputs may vary. This is TB, QB, QB dash, and then this is TC, QC, QC dash. First we'll form the inputs. For PA it is BC, right? So we'll take output of B here, and then we'll take the output of C. We already know that the value stored in the flip-flop can be taken out through the corresponding outputs of the flip-flop. Okay. So BC, no. So BC means it should be 100. This is TA. What is TB? TB is B dash plus C. So B dash means that it is taking its own complemented input as one of the inputs. Then C, right? C is coming here. We have to take it. Then we have to give it to an OR gate. Okay. So B dash plus C. Once again, you should not misinterpret that. We should take the normal output of B and then we should give it to an inverter for B dash. Okay, we can directly take it from the complemented output of B. Okay. Then what is TC? TC is A dash plus C dash, right? That is A dash plus C dash into B, correct? Yeah. Plus B is 100 now. B into A dash plus C dash. A dash means we have to take the complemented output of A, right? And C dash. We will take like this. It could be very clear. A dash, then C dash. Okay. go by like this. Okay, so A dash is given here, and then C dash is also given here, so it becomes A dash plus C dash. Then that should be given as an input to and along with the B. So this is our TC, right? This is our TC input. Okay, then we should not forget that it is a synchronous counter that should be applied to all the flip-flops simultaneously. Okay. The bubble represents that the changes will get affected in the flip-flop during the negative transition. Okay. Then the output will be available through the corresponding normal output. Is it clear? So this is the circuit of an counter that generates the sequence 1, 3, 4, 6, 7, 1. Now we will verify with the this design. Okay. What is the first state? 1. That is nothing but 0, 0, 1. Okay. 0, 0, 1 means what you will be getting. You can draw it in a better way. It's not a way to draw it. Now it's okay. This is an OR gate. Okay. So 0, 0, 1. Okay. Now we need to find the inputs for all the flip-flops. Then we need to apply the clock pulse. Then only the flip-flop will respond to the corresponding inputs. Okay. TA is BC. B is 0. C is 0. So B into C means it is going to be 0. Here this is nothing but B dash plus C, right? This is B dash plus C. What is B dash? B dash is itself 1. C is also 1. 1 plus 1 is 1. In OR gate, if any one of the values is 1, the output is 1. So 1. Then what about TC? TC is B into A dash plus C dash, right? So B into no, right? Then B is 0. So automatically TC is going to be 0. Now, while applying the clock pulse, what will happen? 0 means what? 0 means no change. So this 0 will be retained as it is. Okay. 1 means what is the 1 in T flip-flop? Toggle state. So 0 becomes 1. Here this flip-flop is having an input 0, so no change. So the next it is moving on to next state called as 0, 1, 1. With these values, we need to find the next state. Okay. So we need to find the fresh inputs for all the flip-flops. Then we need to apply the clock pulse simultaneously. Okay. So now TA is having a expression of BC. So BC means 1 and 1, both B and C are 1. So output is going to be 1. Okay. Then what about B? B is nothing but B dash plus C. B dash is nothing but what is B dash? B dash is going to be 0, but C is 1. So it is given through an OR gate. So TB input is going to be 1. Okay. What about TC? TC is B is 1. B into A dash plus C dash. What is A dash? A dash is 1. C dash becomes 1. So if any one of the values, A dash is 1. C dash becomes 0. But A dash is 1 now. So if any one of the value is 1 in the case of OR gate, the output is going to be 1. So both the inputs of AND gate are 1. So TC input is going to be 1. Okay. Now we are going to apply the clock pulse simultaneously. What would be the output? 1 means toggle state. So 0 becomes 1. Here also 1 becomes toggle state. 1 becomes 0. Here also 1 toggle state, 1 becomes 0. So now it has moved on to the state called as 4. That is 1, 0, 0. Okay. With this value, we need to find the fresh inputs for finding the next state. Okay. TA is BC, so B and C is 0. So automatically TA input is going to be 0. What is TB? TB is going to be B dash plus C. So B dash means B dash P is 0 here. So B dash means 1. If any one of the value in the OR gate is 1, the output of OR gate is going to be 1. So TB input is going to be 1. Okay. What about TC? B into A dash plus C dash. But B is itself 0. We need not to bother about A dash plus C dash. So the output of AND gate is going to be 0. Because B into A dash plus C dash. B is already 0. So TC input is going to be 0. Now while applying the clock pulse simultaneously, what would be the value? 0. 0 is input of T. So for T input is 0, no change. That is 1. Here the T input is 1, so toggle. This is going to become 0 becomes 1. Here TC input is 0, means no change. What is the next state? So it has moved to the next state called as 6. From 4 it has moved to 6. That is 1, 1, 0. Okay. With this input, we have to find with these values of flip-flops, we need to find the fresh inputs of flip-flops for finding the next state. Okay. BC. TA becomes BC, but the C is 0. So if you are performing an AND operation, TA input becomes 0. What is TB? TB is nothing but B dash plus C. What is B dash? B dash is 0. Because B is having a value called as 1. C is already 0. So input for TB is going to be 0. Because both the inputs are 0 for OR gate. If both inputs are 0, our output is 0. So the input for TB is 0. Okay. What about TC? TC is B into A dash plus C dash. B is 1. A dash means it becomes 0, but C dash means it is 1. So what will happen? Both the inputs of AND gate becomes 1. So output of AND gate is 1. So input of TC is 1 now. Okay. Now all the inputs are ready for the flip-flops. While applying the clock pulse, what will happen? 0 means no change. So 1 won't be changing. It will be retained as this. Here also 0. No change, so the 1 will be retained. Here the input for this flip-flop is 1, so it will behave like a toggle state, so 0 becomes 1. Okay, so now it has come to the state called as a 7. Okay, that is our last state. Now we have to see whether it is going back to the initial state called as a 1. That is our reset state. Okay, now we will find it. B and C both are 1, so TA input is going to be 1. B dash plus C, right? B dash is going to be 0, but C is going to be 1. So TB input is going to be 1. B into A dash plus C dash. B is 1, but A dash means 0. C dash is also 0. So what will happen? So 1 into 0. So it becomes 0. Now while applying the clock pulse, what will happen? 1 input. If T input is 1, toggle state. So 1 becomes 0. Here also the input is 1. So toggle state. So the 1 becomes 0. Here the T input is 0. No change. So it comes back to 0, 0, 1. Nothing but our initial state or reset state called as a 1. This is how you need to design the counter and you need to verify the counter. If you are not able to generate if your counter is not generating the design sequence, you have to look back to your Kmap simplification, or otherwise you need to look back your input sequence arrangement and the excitation table. You would have committed mistakes in any of the previous steps. Okay, it can be easily verified. You will definitely get a compulsory question in this design of counter, and you can design any counter like this. Okay, it is not necessarily be a modulo counter. Okay, that's what we have seen in the previous session. Now we have seen that the counter can generate sequence in any order. Okay, and one more counter called as an n-bit counter that can also be designed. Okay, n-bit counter, what it means? N-bit counter means it will generate the values from 0 to 2 power n minus 1. For example, if you are asked to design a 3-bit counter, so what is this sequence? Simple. It is going to generate the values from 0 to 7, starting from 000 to 111. Okay. If you are asked to generate a 4-bit counter, it is nothing but 0000 to 1111. 4-bit means 4-bit value, starting from 0000 to 1111. Okay. Similarly, they may ask in any kind of counters like BCD counter. BCD counter means what it will do? It will count from values from 0 to 9. Obviously, it will be a 4-bit counter because 0 to 9. So, how many bits are required to represent 9? 4 bits. So, you need to make use of 4-bit counter. Okay. BCD counter is otherwise known as decade counter or decimal counter. Okay. So, this is about the various ways of designing the synchronous counters. And one more important point you should know is, if you are asked, if they will be specifically they will be asking specifically that design synchronous counter, design 3-bit synchronous counter, design BCD synchronous counter means you should go with this model. How we have discussed so far. You have to take the help of an excitation table, followed by you have to construct the input sequence, and followed by you have to simplify the expression for each and every flip-flop inputs using Kmap, and then you need to end up with the design of a counter. If you are asked to design a synchronous counter, you have to follow the sequence or follow the discussions that we had done in the 2 sessions. Okay, it is very important because there is a difference in designing an asynchronous counter. Asynchronous counters designs we will discuss it in next class.